welcome to FlexAlloc, a lightweight building block for user space data management. My name is Jesper, and this talk is delivered by myself, Joel, and Adam, all of us from Samsung Memory. Let's review the agenda. In part 1, we start with our central observation, which inspired FlexAlloc. We then take a step back and recap the characteristics of Flash media and examine how both hardware, software, and interface layers have changed following its adoption. We then briefly review the options available to storage developers today and introduce FlexAlloc. In part 2, Joel then delves into the design of FlexAlloc in greater detail, explaining how the allocator works and its principal data structures. Finally, in part 3, Adam demonstrates the flexibility of FlexAlloc by building a named object abstraction on top and building both a RocksDB environment and a FuseFS file system on top of that, demonstrating how on the system we can run a RocksDB workload and how data can be read back out via the Fuse file system. So, this project started with us endeavoring to create a system providing a fast NVMe native write path with minimal overhead. This meant stripping out most responsibilities and features of a modern file system. For compatibility, we wanted read-only access via a file system interface, permitting interoperability with established tools for DevOps and making backups and so on. During the design, it became very clear how, for each feature, we were making multiple decisions impacting any client application using our system. In case of naming, must all systems pay for the overhead of naming? Must all objects be named? Which indexing structures should we use to handle lookups, and when should they be synchronized to disk? How long should names be permitted to be? Implementing naming would serve our immediate use case, but it would be useless for other applications, building a base layer, for example, for a data store. Simply put, there are no free abstractions and there is no free lunch. Existing layers in the software stack, such as file systems, are complex, well-designed components, but their foundations date back to an era of storage devices radically different from those of today, namely spinning drives, and they are built on top of the block interface. Today, applications face an all-or-nothing proposition. Either you adapt the file system, preferably one whose trade-offs fit well with your workload, and you pay for all of its abstractions, or you opt out and you're faced with re-implementing all these abstractions yourself from scratch. In this talk, we introduce FlexAlloc, our take on a smaller compositional building block for storage applications, desiring a lean allocator with a high-level object storage interface whose operations are written to take advantage of NVMe devices using the NVM and ZNS command sets. Before going any further, however, let's review how did we actually get to this situation. The introduction of Flash meant a fundamental change of the underlying device characteristics. With traditional spinning disk drives, a single stream of sequential access requests is optimal. Conversely, flash drives are much less sensitive to random I/O and in fact seek to distribute data across the device to achieve optimal performance. However, other characteristics changed too, namely overwriting was no longer supported. Reprogramming a flash page requires first erasing the entire parent block, consisting of many pages, in some cases as much as 256 flash pages. To still masquerade as an ordinary block device, the flash drive comes with a flash translation layer, or FTL, to transparently map logical to underlying physical blocks. The FTL also conducts garbage collection, selecting blocks to be erased and migrating still live data to pages in other blocks, all while trying to use blocks evenly, as flash media will wear out after a certain number of erase cycles. On the hardware side, as flash drives matured, existing interfaces like SATA became a bottleneck. We went from SATA to PCI Express using the NVM Express specification, or NVMe for short. Throughput changed from 600 megabytes per second, single or half duplex with SATA, to just about 2 gigabytes per second on a single PCIe 4-lane. Similarly, where SATA has one hardware queue with a depth of 32, NVMe assigns one submission queue and one completion queue to each CPU core, but supports up to 64,000 queues, each with a queue depth of 64,000 items. NVMe also introduced the concept of command sets, groups of operations collectively forming an interface. The initial command sets were the admin set for device and queue administration, and the NVM command set offering basic I/O read and write commands. But more exist. Some expand on the block interface, like the zoned namespaces command set, while others are an alternative to it entirely, such as the key value command set. On the software side, we also saw a huge impact by the adoption of Flash. On Linux, for example, the I/O scheduling component of the block layer was redesigned fundamentally to leverage the increased parallelism and number of hardware queues of modern storage devices, such as NVMe devices. Another goal was reducing lock contention and cache thrashing. BlockMQ allows each CPU core or socket, you may configure this, to get its own staging queue, which is roughly analogous to an NVMe submission queue. And these eventually map to a number of hardware dispatch queues, which buffer work until it can be dispatched to the device's hardware queues. At another layer in Linux, IO-Uring is conceptually also very similar to the design laid out in the NVMe specification. IO-Uring is also modeled around a series of submission and completion queues. Additionally, IO-Uring amortizes the cost of system calls by allowing the user to queue multiple requests before triggering processing, and it avoids copying memory from the application and the layers down by memory mapping these I/O buffers. Finally, we also have seen the introduction of SPDK across the platforms. SPDK, or the Storage Performance Development Kit, is a pure user space I/O stack using message passing rather than locks to control things. It uses polling rather than hardware interrupts. Because it's entirely in user space, there are no system calls being made and thus no overhead from traversing from user space to kernel space. And similarly, it also achieves zero copying of the I/O buffers. So in summary, Flash has been impacting all layers of the stack. As NAND adoption grew, bottlenecks have shifted toward the software layers. Specifically today, we're concerned with the kernel to user space context switching overhead, syscall overheads in general, hardware interrupts, and block contention in the block layer. NVMe supports multiple interfaces. Some expand on the traditional block interface, others supplant it. After more than a decade of optimizing other parts of the stack, the interface is now being examined in earnest. Another important thing to observe is that we're seeing a redistribution of responsibilities among these different layers in the stack. Originally, we retained the block interface, but by doing so, we hid the device properties behind that interface. That's where we get the Flash translation layer, the garbage collection, and so on to bridge the gap. The zoned namespaces command set that was recently introduced is one of several attempts at optimizing the stack by simply redistributing the responsibilities between the device, the operating system, and the application. So if we were to build an application today, what would our options be? We're centering this review on Linux, but it's pretty similar. So today, storage applications are typically sitting on top of a file system, which handles data placement and organizing the disk's blocks into files and directories. In case of Linux, there are 3 APIs for reading from and writing to the device: the traditional synchronous I/O system calls, and 2 APIs for asynchronous I/O, with IO-Uring being the newest abstraction. Regardless of which of these paths you take, your IOs are going to go through the block layer. Specifically, we start at the bio layer, or block I/O layer, where each bio is associated a single contiguous range of blocks. The bio layer may split or merge these bios, and it may also plug them, meaning they're temporarily withheld in hopes of incoming bios, which can then be merged to form a larger request. These bios are eventually submitted as requests to the request layer, where typically the block multi-queue scheduler, which we discussed earlier, may merge and reorder requests before submitting them to the device. Increasingly, modern devices also provide additional operations that are defined beyond what is defined by the block interface. These are exposed typically as ioctl commands. The libnvme and libsetbd libraries provide wrapped ioctl calls for managing NVMe and zoned namespaces devices, respectively. So, file systems today are very well designed, but the permissiveness of the interface puts the file system at a disadvantage when making allocation decisions. A file may be 2 kilobytes or 2 gigabytes in size, and it may grow or shrink arbitrarily during its lifetime. While pre-allocating larger ranges of space is indeed possible, it is not required, nor need the file system actually obey such requests. File systems typically allocate in units of blocks or extents, but as the file system ages and fills, finding larger contiguous free block ranges become increasingly difficult, forcing it to allocate several smaller ranges, which causes fragmentation of the file. This fragmentation also incurs a lookup and translation overhead, as writing to a logical byte range within the file requires translating that range into one or more of these underlying logical block address ranges. Finally, file systems are large and complex systems. They implement the OS-mandated file system API, and they tend to support many kinds of block devices, SSDs, hard drives, SMR drives, and to varying degrees they take on additional responsibilities such as encryption, RAID, and more. Consequently, these systems may take a while to take advantage of newer hardware developments and may not always be able to do so optimally due to the existing design trade-offs. In essence, larger monolithic systems with many assumptions baked in will at best take longer to retrofit for new storage design paradigms, and at worst be unable to exploit them fully or at all. So if not a file system, we could consider using the block device directly. Using the block device directly, you would gain greater control and could in fact capitalize on new developments such as the zoned namespaces command set by issuing ioctl commands to the device directly. However, you would need to design a data placement scheme yourself, and in case of ZNS support, take care to obey the additional constraints imposed by such devices. Using the block device directly, you would still have to decide which of the system's I/O APIs to use. Similarly, with modern devices, the block interface abstraction is simply insufficient, and so you would require some method like ioctl calls to perform additional operations like configuring the NVMe device, discarding data efficiently zeroing out block ranges, or managing zoned namespaces zones. FlexAlloc is intended as a building block, as an alternative to this, for storage applications. FlexAlloc provides efficient data allocation with minimal overhead. By using a slab allocator design, mandating that object size is fixed and determined by its class or pool, we can drastically reduce metadata overhead from indexing and allocation structures. Instead, object locations can be computed directly from the superblock and their object ID, and all objects are essentially a single extent. Furthermore, FlexAlloc uses an object storage API instead of the block interface, and the underlying implementation makes full use of NVM and ZNS command sets to work efficiently with conventional and zoned namespace NVMe devices. You may also note from the diagram that we use a layer called XNVMe, which sits in between FlexAlloc and the device. XNVMe is not strictly speaking necessary, but we have chosen it in our current configuration because it's a very useful abstraction that allows us to communicate efficiently with NVMe devices regardless of the underlying operating system. So by using XNVMe, we're gaining support for Linux, FreeBSD, and Windows support, which is upcoming. Additionally, we can also use SPDK through this layer if we so desire. FlexAlloc itself is just an allocation layer. We can make changes to become a layer within the kernel, for example. But for now, using XNVMe has been a delight, and we highly recommend that you look at xnvme.io for more information. And this is the end for me. and now Joel will take it from here.
Thank you, Jesper. Now let's talk about the FlexAlloc design in more detail. We will lay out this section in 4 subsections. First, we will discuss how our motivations inspired our design. Then we will describe FlexAlloc's design in detail, followed by some interesting characteristics that are somewhat unique to our allocator. Finally, we will discuss 2 projects that have very similar objectives to ours. So let's contextualize the motivation within the design. FlexAlloc provides versatility through XNVMe, which translates into being able to use different backends like IOUring or libaio, and different OSs like Windows, Linux, or BSD. It is part of a layered storage stack. If an application needs more functionality like naming, compression, or encryption, then it has to add these on top. They will be provided by other components in the storage stack. We assume very little in terms of implementation, as opposed to a file system that has to make countless assumptions of what type of naming to provide or how compression might be implemented, for example. By relegating all the additional non-essential functionalities to other components, we maintain a lean layer. We do one thing and we do it well. FlexAlloc is heavily inspired by Bonwick's slab allocator. And one of the observations set forth by Bonwick is that the allocator should not be making any assumptions of the allocated memory. The application would be the better judge of how big the allocation should be. We took this and translated it into how file systems are making all sorts of decisions without really considering what the application has to say. A better approach would be to give control back to the application by making it part of the requirement definition process. Being a lean layer comes with the added value that we do not need lots of metadata. The few structures that are needed for FlexAlloc can fit in a few free lists and hash tables. Now we delve deeper into the design. We basically separate the device into metadata and data. The data is held in a structure called a slab. The rest of the device after the metadata is used by these slabs. Slabs are contiguous sets of logical blocks, and all slabs are of the same size, and this size is decided at format time. Each slab will hold a set of objects and has minimal metadata to keep track of these objects. A slab can only contain objects of the same size. As you can see in the figure, all the slabs holding object 1 cannot hold any other type of object. This allows us to calculate the metadata size of each slab quickly. Within the slabs, we have objects, which is the currency of FlexAlloc. We do not follow traditional block allocator design where objects are artificially fragmented all over the device. Instead, they are contiguous sets of logical blocks on the device. Objects live within a slab, one after the other, and with an additional section reserved for metadata at the end of the slab. As you can see, the light blue section for each slab. Once the object is allocated, FlexAlloc gets out of the way and lets the application decide what to do with the range of logical blocks. For each object, the application sees a range of blocks that starts at 0 and extends until the selected size. Read-write operations are executed on these ranges. FlexAlloc simply translates the object ID into a logical block offset and passes the read-write operation along. So the objects are grouped into pools. Pools bind slabs that hold the same type of object. They keep track of which slabs are free, which slabs are partially filled, and which slabs are completely full. They only hold slabs of the same type, which in turn hold objects of the same size. In the figure, we see 2 different pools. Pool 1 holds objects that are smaller than Pool 2. Pool 1 has 2 slabs for its objects, whereas Pool 2 has just 1. The slabs that are not related to a pool are used when a pool runs out of free slabs. Finally, pools hide away the slab structure from the application. Everything is kept in check by the metadata, which is located at the beginning of the device. In this figure, you see it represented as red, purple, and orange squares. And remember that there is also a bit of metadata in each slab, which is represented by the light blue stripe in the figure. Most of this metadata is defined at format time and contains information related to the drive itself and information used to keep track of where everything is. Now let's talk about some characteristics, and let's start with some characteristics related to size. The object size is defined when it is created, which means that it can't be exceeded. As mentioned previously, the object is also contiguous and is not fragmented. This reduces the metadata needed to handle the objects, and it also reduces external fragmentations, as there are no calculations by the block allocator on how many additional blocks are assigned to the object. The internal fragmentation, on the other hand, is fully under the control and responsibility of the application. FlexAlloc gives all the power back to the application, which defines the size and is responsible for using it. FlexAlloc effectively changes the way objects are used. You go from just creating one to actually thinking about its lifetime. This, hopefully, leads the developer to be more careful with the design, as the interface doesn't allow objects to go over a predefined size. Our vision is for FlexAlloc to be part of a heterogeneous and versatile storage stack. So if you absolutely need a traditional allocator not bound by object size, you can easily build one on top. Both the number of slabs and pools are predefined at format time, which allows for two things. One, to know exactly how much metadata is needed for each, and two, it provides tunable parameters so the application can configure the allocator for its particular needs. Now let's move to other characteristics that are not necessarily related directly to size. Like the object ID handle returned to the application can quickly be translated into the actual logical block with just a couple of arithmetic operations. So the transformation is quite fast. FlexAlloc's structure provides a setup to support both conventional namespace and zone namespace. Conventional namespace is quite easy, as we just have to handle a set of logical blocks. Zone namespace, on the other hand, is tricky, as we have to have considerations with zone sizes, right pointers, number of open zones, and so on and so forth. But our slab object abstraction facilitates zone namespace implementations, as we will see in the demo. Though we have a minimalistic design, we pack a lot of punch in that we sit on top of XNVMe, which gives us the versatility of choosing OS and also backend. Actually, you can even choose to ignore the OS completely and by using SPDK. Now let's list two projects that are related to FlexAlloc. We go through some projects that have a certain degree of overlap with FlexAlloc. Here we mention a couple which show how the industry is moving towards designs that share FlexAlloc's vision. We start with BlobStore. BlobStore is defined as a block allocator, which is a subcomponent within the SPDK project. It's designed to be a thin layer within the SPDK storage stack. It serves as the base for other services like BlobFS, and it sits on top of BDEV, which is a block device. A key difference with FlexAlloc is the format used for BlobStore. It has more of a traditional block allocator design, as it's based on clusters, and these clusters grow as the blobs grow. Then we have BlueStore. BlueStore is designed as an object store and is part of the Ceph project. This means that BlueStore is envisioned as a bigger project than FlexAlloc and encompasses more functionality like compression and checksumming. It is tightly related to the KV store RocksDB, where it uses it to manage the metadata in the allocation. This moves away from BlobStore and FlexAlloc, which use RocksDB simply to exemplify their use. That's it for the related projects. And now I'll hand it over to Adam so he can tell us a little bit more about how FlexAlloc behaves in the wild.
Thanks, Joel, for the handoff. In this part of the talk, I'm going to give a demonstration of FlexAlloc running on top of a ZNS device and how FlexAlloc is integrated into an application that will be RocksDB. And this part of the talk is broken up into two sections. The first being overview of why we chose ZNS as well as why we chose RocksDB. and then a little bit more detail about how we integrate ZNS inside of FlexAlloc, and then I'll end with a demonstration of what we currently have. Okay, so when this particular slide, I want to bring attention to RocksDB at first. And so if you're not familiar with RocksDB, what it is an embeddable key value store. So this means that it's a library that you link to your application and you make calls into this library from within your application. It's not a client server architecture. The interesting thing about RocksDB is that it leverages DRAM, as you can see in this architecture figure, to write all incoming KV pairs into what is called a mem table. And so it organizes these KV pairs sequentially, and then eventually transforms them to an immutable copy in memory. And then it actually writes this data sequentially out to the disk. And these KV pairs are organized sequentially. And so it writes these KV pairs out sequential, and also it rewrites them out all sequentially to storage. The interesting thing about RocksDB is that the backend to storage is currently modeled after a POSIX-based environment, but it is a pluggable component of RocksDB. And we have examples in RocksDB, such as the HDFS environment, to draw inspiration from. The second key thing on this slide is talking about ZNS. And so what ZNS is an extension to NVMe. And the key distinction is that the namespace is now broken into contiguous LBA ranges, which is called the zone. And these zones are typically mapped onto SSD dies to give you some control over SSD behavior. So you're able to separate writes and reads from your application level to influence device behavior. A key caveat of a ZNS SSD is all writes must be at the tail of a zone. So this forces sequentiality to the device. And so we wanted to marry these two concepts together, is that RocksDB is largely sequential and zone namespace devices require sequentiality. And so how do we marry these two different pieces together, right? We have the application as well as the SSD. And one thing I'd like to draw attention from this figure of the ZNS SSD is that in order to support it in say, a modern OS like Linux, there is a lot of work that needs to be done to update applications, file systems, device drivers. This is all different pieces that have to be changed in order to support ZNS SSDs. And another way of trying to go about this problem is to try to actually use raw block device access, and that's where FlexAlloc comes into play. Right, it sits one layer above the device, and we want to integrate RocksDB with FlexAlloc, right, and so that we have a user space component that is able to manage the ZNS SSD. And so FlexAlloc itself currently implements support for ZNS. And it's a lightweight support in that it aligns slabs and objects to zones. It also manages opening and closing of zones, but it doesn't sequentialize writes for you. The application has to write sequentially to these objects. And that's why we chose RocksDB, since this application actually sequentializes IO from the beginning. So we've developed this RocksDB environment for FlexAlloc. And in the beginning, we actually developed this component of RocksDB that connects to FlexAlloc independently of the ZNS support. And then we had minor changes to update it to actually when we added ZNS support to FlexAlloc. So it's been a nice success story where we could build these components largely independently. In addition, we've created a read-only fuse file system. And so this is to be able to pull data out of the ZNS SSD or any storage device that is using FlexAlloc, so that you can be able to read the data back out and copy it onto a traditional file system if needed. All right, so now I'll switch gears and actually start showing a demo of FlexAlloc running on top of a ZNS SSD and with running a RocksDB consuming FlexAlloc. All right, so I'll draw your attention to this screen here. And so what we're going to do is we're going to run this Rocks demo. And there are some files here just for setup or just cleaning up things that were previously there. But the first command that I want to draw attention to is the makefs.flexalloc. So we now have a makefs command, and we say the size of the slabs, the number of pools. We're going to use a metadata device. So we're able to use a metadata device for in-place updates that is separate from the ZNS SSD, as well as the ZNS SSD itself are provided as arguments. And so we create the file system with this first command. After that, what I'm going to do is list all of the zones on this device. So we use the xnvme zone report command on the zone ZNS device, and I'm only showing the 16 most recent, or the 16 zones starting from 0. And as you can see, all of the zones are empty. And we've initialized the device because we're not, this is where all the data will come from, and all of the metadata is currently inside of the secondary device. So we start with a clean slate. Now I'm running RocksDB with FlexAlloc support. And so the things to here is I'm doing a fill sequential workload. I'm going to do 512 KB pairs, and that's a value size of 4096 bytes. And we're actually using FlexAlloc, so I supply the device, which is the ZNS device. I also set that we're going to be using FlexAlloc, and also supply this metadata device. And so we're able to write all these 512 KB pairs successfully in this benchmark. All right, now what I'm going to do is I'm going to relist the zones from the ZNS SSD once again. And so what we see here is that we have some zones are full, some are implicitly open, but we've now utilized this ZNS SSD while running RocksDB. Okay, so I want to show a directory here. This /mount is this directory I'm showing on the host, and there's nothing inside of it. Then what I'm going to do is mount this FlexFuse component. So FlexFuse was our read-only file system. And so again, I passed the ZNS SSD as well as the metadata device and give it the pool name that was used by RocksDB. Also, the object size is passed to this file system, and then I give it this /mount point. Then when I relist the files in this directory after mounting our FlexFuse, then we see all of the files that RocksDB wrote. There's SSTables files. There's also metadata that was written by RocksDB. And currently we don't store permissions as well as access time. And so this is just filled in by default by Fuse currently. All right, so I want to now show you that there's nothing inside of the /temp/db directory. Then what we're going to do is copy from this mount point that has the data from the ZNS SSD into this /tempdb. Then I'll re-show this directory once again one more time. And then now we see that all the data that was on the ZNS SSD is now on the local file system. And now we do have permissions, and we do have access times accurately reported here. And the last step is to restart RocksDB. And so I use this use existing DB, give it /temp/db so that we restart from the host file system here. And what we see is from this output that we're able to successfully find all 512 KB pairs. So this was a successful run of writing the data through a ZNS SSD using FlexAlloc, and then copying the data to a local file system that's a conventional file system, and then restarting RocksDB from this data here. So let me switch back to presentation. So the last section here is a summary of our talk. And so what we want you to take away from this talk is that FlexAlloc is a lean and flexible block allocator. We see it as a building block for user space file systems, and we would like people to use it instead of building user space file systems from scratch. We believe this low-level flexible block allocator can be reused in other user space file systems. An interesting point about it is that we currently support ZNS. So if people are thinking about creating file systems for ZNS, it could be a good starting point for building your ZNS application. It leverages xNVMe, and this provides flexibility for device access. So you could use async interfaces, sync interfaces. You can also support different OSs such as Windows or Linux. And it also supports SBDK, so giving you access to a user space driver if that's what is necessary for your application. We've prototyped our RocksDB integration along with this read-only Fuse mount, and we're going to continue to work on this and develop this RocksDB component and to develop this application as we see fit. And we're hoping to open source this in the near future. And we thank you for your time for listening to our talk.